Welcome everybody to Optimization in Oslo today on a Tuesday. We're very happy to have Professor Alfio Borzì from University of Würzburg. He's going to talk about quantum models and optimal control problems, and as well as some open problems in the area. So Alfio.
Okay, thank you very much, Thomas, for this kind invitation. I was one time in Oslo. I hope look forward for next time, but now is lecture time for me. It's very difficult to come in person. So we use this new modern way to give talks. But please interrupt me or ask any question during the talk or afterwards, or even later. I will be very happy to share ideas and discuss problems. Okay, so the topic of this talk is quantum models, because in fact there is a variety of models in quantum mechanics, from finite dimensional to infinite dimensional, from linear to nonlinear, and many of these models require different methods to solve or to approximate. And the purpose for the control is to manipulate these models to get something done. So it is it's theoretical, but it's straight to the idea of making applications. Okay, so the possibility for control, which usually is the potential or part of the potential on the Schrödinger equation, is to induce or drive state transitions, maybe make some chemical reaction happen, or make some trapping like in Bose Einstein condensate. Then there is okay, the future is quantum computing, although we still do not have a quantum computer, but the essential idea is how to manipulate systems, qubits, to make this happen. In a more larger scale or more macroscopic, like quantum transport, Bose-Einstein condensates, superfluids, and vortices. This is something very beautiful where there are also many experimental results. Then there is like magnetic resonance imaging, quantum optics, and semiconductors. So these are all topics where quantum control is today being used. And for sure, there are many more that I cannot imagine at this point, but the list could be very long. Okay, so I just want to come to the first point when you say what has been done or not. Well, there are 9 different formulations for non-relativistic quantum mechanics. I also didn't know that when I wrote the book. But of these 9 formulations, we are used to wave functions and to density matrices. There's almost nothing in the other formulations. So this is one point which is open for research, is to investigate if there are other formulations where the control theory and control systems can be better analyzed or understood. Another thing where there is nothing, I mean, this is my personal knowledge, so I'm ignorant on this topic. So I'm just my feeling that there is nothing in relativistic quantum mechanics. There are also physical issues for that. For example, what is a time-dependent control in this case? And this leads to the question, what will be a time-dependent field theory? So as far as I know, there are very, very few works on time-dependent field theory anyway, and no works with control. Then, as I said, wave function density matrix is what we will talk today. And in this sense, this already makes the field of quantum control wide open for research in the next 100 years. Okay, so just to see which kind of model I have considered and that are maybe better known are in the Schrödinger formalism with the wave function. So from one particle Schrödinger equation in a box to the mean field kind of Schrödinger equation, which is the Gross-Pitaevsky equation for Bose Einstein condensate. And then there is the non plus ultra Schrödinger equation for multiparticles. And actually this is scalar, but there is also the spinorial version of this, which will be the Pauli equation. Then the issue of the last equation, the one with the many particles in Schrödinger formalism, is intractable by any supercomputer. If you go beyond, say, five particles. So there is an alternative approach, which is more statistically based, which is the Kohn-Sham equation. This is a very well-known model in computational and theoretical chemistry. And I hope we will have time to see in detail this equation. Then at the level of one particle, but a statistical representation, we have the Wigner equation. This is very close to what is, say, Vlasov collision equation, or also without collision. And these are all infinite dimensional models, so they are PDEs. On the other hand, it is also a very large field of research with a lot of results in control theory are related to the Liouville-von Neumann equation, which essentially the one you see, it is actually an ordinary differential equation because it is considered for finite level, for say 5-dimensional systems, but in the field of QDITs, the number cannot be very large. So actually, I think N20 is the largest point number at this point. Okay, and there are also other variations. These are all closed quantum systems. If we consider open quantum systems with the Lindblad operator and possible measurement modeling by stochastic terms, then we come to stochastic Schrödinger equations, etc. And then this is, again, another field of research. So in many of these cases, almost all of these cases, it is always possible to find a representation in mathematical terms so that the evolution is first order in time, and we have a free Hamiltonian, which in this picture you see here is the matrix A, and a matrix control term, the matrix is called a dipole matrix, sometimes a control matrix, which makes the link between control functions and the state. In this case, the vector x. It can be a numerical approximation of a wave function or the exact representation of spin levels or whatever. You see that here the control always multiplies the state. So we always have to do with the so-called bilinear control problem or control affine problems. So in addition, in the quantum case, the matrix A is Q-symmetric and the Bn can be, or actually R as well, because you need the unitarity of the evolution, unless you have an open system. Well, even in the most complicated case, which is, I mean, for one spin system where you have a magnetic field and electric field, so you can always put this in the first form. So the equation below, we can use this to derive the one written on the first line. Okay, so as you see, the control functions are essentially potentials or modulating functions of potentials. So the control is always about potentials, as far as I know, although it would be possible to have control like, say, controlling the flux of an inlet of quantum particles, things like this, through some transmission operator. Anyway, in this field, the control will be then an electromagnetic field, and in many cases, it is essentially a laser pulse. As you see on the bottom of the slide, so we will always think of a potential, a general potential, time-dependent, where the non-time-dependent part is usually the one for the free Hamiltonian, the one which is making the confinement. And the control will be some function of space and time. So in the dipole approximation, the first order, it is x time ut. So this is about the models. Then there is a point what we would like to do with these controls. And well, actually, one classical problem is to let the system go from one energy state to another energy state. So the energy states are eigenfunctions of the Schrödinger equation, the stationary equation, and the energy values are the eigenvalues. So the simplest, the most investigated case is transition from one state to another, that is from an eigenfunction to another one. In this field, there is also the topic of controllability, which actually I will not talk about here, but this would be a subfield in this case. But we can have more practical issues like you have a molecule, you want to break it with minimal energy, so break a bound in chemistry, or you want to maximize one of the observable. So observable, as you know, in quantum mechanics, is the expectation value or the integral with psi bar psi of some quantity which is represented by an emission operator, which is called O in this case. And here, if we go down on this level, we can also think of designing structure like quantum gates, which will be to optimize performance in some device at the quantum level. So nano devices, say. Okay, the structure, so we have seen the model, where the control is, we could ask for, and this last part must be encoded in the formulation of a cost functional. So the cost functional in quantum mechanics, as in many other fields, is usually has two pieces. One has to do with the state, and one has to do with the control. So the one of the control is about the cost of the control. Most used is L2, so just a quadratic of the control function. But it would be interesting to look at different ones which have really the meaning of energy. So U square is not energy in any sense. And the other part of the functional, J1, is about the requirement that we told before. Maybe get to some final state. So maybe maximize the observation or the value of observation function, etc. And in addition, we can also ask to have constraints on the control by requiring to be in some admissible set, okay? So the formulation of the control problem is like the formulation, in the quantum case, is exactly the same as in any other field of control theory. You want to minimize a functional or maximize it subject to some differential constraint. And this is the beginning of the story of quantum control, actually. No, anything that can be written this way, where the model is a quantum system, is a quantum control problem. And well, actually, I think you know all this better than me, but I mean, the procedure is therefore to go through some steps or classical steps to guarantee existence of controls and maybe uniqueness. Uniqueness is almost never obtained in bilinear cases. Actually, in quantum systems, because of some quantum symmetries, it is almost always that you get twice the control. I mean, it comes in pair almost in all cases. Yeah. So to do this, what we do, we put this problem in a, say, standard optimization problem by introducing the control to state map, which means that we just analyze the fact that fixing the initial condition, we give a control and we get a state of the system. No, you can choose any control function, just your choice, and it will give a quantum trajectory. So if we have this map, we can rewrite the system in a reduced way, so call it. So you realize encoding the dependence of the state with the control in the functional, we actually have a functional of only the control. So now it's a standard optimization problem, still infinite dimensional because we look for functions. And indeed, there are many works where this control is parameterized. This is because of some knowledge of perturbation theory in quantum mechanics. You know that for some transition, your function must have some frequency structure. So you can also do parameterization, and then it will be a finite dimension problem. But this is not so challenging for mathematics, okay? So let's go on with this. And once you say, okay, I've proved everything of my model, given the control U, I have my state. This is not trivial because most results available, for example, say require that U is a very smooth function, but in control it can be discontinuous. So even this basic question, there will be work to do in many cases. But supposing you have done this, then you have existence of controls. Then you would like to compute them, and the next step is to derive an optimality system, which on itself is a characterization of the control, but it is also the way we can solve it numerically. So you write a Lagrange function. The Lagrange function is done in, say, in analysis. You write the function to be minimized plus scalar product of Lagrange multiplier with the constraint. The problem is to pay attention that we are always in complex Hilbert spaces. The Lagrange function is a real function. So this is why we put this real part of this scalar product. So this is a Hilbert scalar product in complex spaces. But this is just a small detail, which is nice to trace back when you derive the optimal system and how you derived it. Well, these are the extremals of the Lagrange function. So if you do this, you obtain again the equation for the state, but you get something new. You get an adjoint equation, which is not always a quantum model. It's not always a unitary evolution. So in this way, you generate mathematical problems that have never been considered, okay? So a lot of adjoint equations have never been studied before. And the third part is the optimality condition, which tells you when the U is optimal. Okay, I'm sorry. So maybe I'm spending too much time in these introductory issues, but now I can make you an example. So this is the first example, and this is the example from Graz. And we talk about Graz. So this was my first work with Ulrich Hohenester and Georg Stadler while we were all in Graz. So this is an open quantum system. So the idea is that you want to have transition from Psi1 to Psi2, but Psi1 and Psi2 cannot be connected physically directly. You have to go through a third state, and in this third state you have dissipation. You lose some part of it, okay? And this is all represented in this picture. And in this case, the evolution is not unitary. So let's see what is the mathematics of this. We have a Schrödinger equation finite dimensional, so it's a set of ODE for a complex vector. The Hamiltonian is a free Hamiltonian plus a control Hamiltonian, so a H0 plus VU. And the control potential is modeled as a dipole control. So I just go to the next slide to specify, well, I think I specified this here. So the free Hamiltonian H0, you see it is an emission matrix, where there is a term I gamma 0. This makes the Hamiltonian not emission, and this is dissipative. So this is not a standard formulation. The control function VU, the control potential VU, as you see, is the submatrix, which is written in, say, dipole form, where you have this mu1 and mu2. These are called the dipole factors, and the U is assumed to be complex. So it's a complex function. So U star is the complex conjugate of it. The adjoint equation, as you see, so this is the optimal system. The first is the model, but the second is looks like an say a Schrödinger model, but you have H star here. So if H is Hermitian, as in many quantum systems, then will be the same. But in this case, not. And then you have this part here, which for sure destroys the unitarity of a revolution operator. So a question like this, even this very simple model, are, say, new to be analyzed. And then the optimality condition written in the appropriate way, assuming H1 cost of the control, will come to this. Okay, I don't think it's important to go through these technicalities, but just to tell you, this is the adjoint, the optimal system, and we have derived it based on a specific functional. So in the functional, this is a very beautiful modeling field, how to write the functional. There is no rule about this, but let's say what we have done here. You wanted to start from some, say, initial condition. This is given, can be the ground state. Then you want to be at final time. You want to reach some final psi t, this one. And this is, in fact, the desired state at the end. Notice that we do not have any tracking functional here, because physically it is quite difficult to explain how you can fix the trajectory in a quantum system. So usually you have final observations, no tracking. And then you would like to minimize the occupation of the state, which is dissipative. So this is term here is the third level, the level on the top of our triangle, where you want to be as less as possible. So you want to minimize this part of the functional. And finally, you want to minimize your cost of the control. So the first one with beta is the classical one used in quantum mechanics, and much less used is to ask for H1 regularity, which actually makes much sense since you want to implement these controls in a laboratory or in a device, and it is not so easy to implement a L2 function, no? Okay, so this is an example how we design a control problem and how we solve it. We solve it by writing the optimality system and then using essentially the optimality system recursively by solving forward the state equation, then the adjoint, and then write a gradient which corresponds to the residual of this third equation, and then update the control and repeat. So this is a gradient method, and then there are many other more sophisticated methods, and maybe we will see Newton method afterwards. Okay, how to read the quantum phenomena in the control problem? Well, you want to be as close as possible to the target state. So this is measuring the target state. So you see there are differences here from 10 to minus 3 to 10 to minus 5, depending on the choice of the parameters. And the parameters are those that explain why we get these numbers, because you see gamma equals 0. What was gamma? You see the control. Sorry, can I jump left and up and down for showing you? So let's see what is gamma. Gamma here is the H1 cost, so the cost in the first derivative. So if I allow for jump, I can do more in quantum mechanics. And this is what I get much better tracking, okay? So more cost, lower cost means less fulfillment of the target that I'm requiring, okay? And the same here, you see, if alpha is larger than 0, alpha was the occupation, penalization of the occupation function. So if I have more penalization of this, I lose less. So I have a better than when alpha is 0, okay? Because this is like a conservative system. So if you lose something, you will never reach again your final state. Okay, so this is just the result of this, for this control problem. This is the control function, the real and imaginary part. And you see transition, you are in the state 2. The first state, say, it goes to 0 and you come up to the second state, okay? So this is just for an example. Okay, so as I said, in the standard quantum mechanic works, the L2 control cost is the used one. It is quite difficult to find papers with other costs of the control, but if you go in the literature of mathematicians doing control theory, then you see plenty of different costs of the control. So this transfer of the usage of control costs from mathematics to physics is, I think, ongoing, but is still not very well developed. So this is something that must be done. And why is not well developed? In many cases, algorithms that are used in many laboratories like Krotov or Grape have not been updated for this kind of cost. So they actually do not work. So this is one point to say something it can be done. And the L1 cost is in physics very important because sparsity is essential in a laboratory experiment, because in laboratory experiment, most of these pulses are designed as, so 0 pulse, then 0. So this is also for the application experiments very important. So L1 controls, and now we try to make a video for a spin system. So actually 2 uncoupled spin 1/2 system subject to the same field. I don't know if it works with Zoom. Let's try, okay? Do you see anything?
Nope.
Ah, no, okay. Okay, let me share. Okay, I do this time, I'm sorry. Where is how to share 2 things anyway?
I think you might have to just open up the other.
Okay, just a second, I don't know. Stop share and then share. Okay, where is it? This one. I don't know how to do this, but I guess if I share this, sorry, I'm very bad in. Oh, now you could see maybe. Huh? So this is L2, L1 control of 2 spins by a single control field. You see the sparsity is that the part where the U is 0 and then jumps actually in a regular way until the spins have been put on down. Okay, so that was just for one. Okay, stop sharing and then I share again. Okay. Okay. Sorry, I hope I'm not too slow in doing all this. Okay, so open quantum system is my next, yes, open quantum system is my next issue, something where there is a lot of mathematics, a lot of theoretical results, much less computation, well, especially if we go in the stochastic world. So the point is this, that quantum mechanics is defined essentially as for closed systems. And the idea is how to say, model the interaction with the environment. And the environment is important because this can be a measurement instrument. So one way to do this, or one approach, is to represent this influence of the environment with a stochastic part. And this leads us to the Lindblad model with some stochastic parts, stochastic noise. This is the Wiener process. So in this case, there's much less done. And the point is how to do control of this. So this is related, or we can go from this Lindblad stochastic to the stochastic Schrödinger equation, vice versa. So there are many ways to do this. And this is one of the few proposed models for qubits with this continuous measurement system. So this is the Wiener process. There are also models with the jumps, and but I'm not discussing this. So what is the idea now? How can we control a complex, say, stochastic process? Well, the idea is to write this in the block sphere and recognize that we have the two essential coordinates, so the spherical coordinates, theta and phi, and obtain like a system of stochastic differential equations. And what I personally have done on this with Mario Annunziato was to consider the Fokker-Planck equation corresponding to this stochastic system, and then implement or formulate the control problem at the level of the probability density function, because we cannot follow all these trajectories. And therefore, we move from control of a finite dimensional stochastic model to the control of infinite dimensional PD model, which is the Fokker-Planck equation. This is a Fokker-Planck equation on the sphere with some special properties because of this. But the important is that the control function on the microscopic model of the stochastic differential equation is exactly going through to the Fokker-Planck equation. So the same mechanism appears in the Fokker-Planck equation. And so we have a perfect correspondence of the two problems. And by working with the probability density function, we actually describe the entire statistics of the model. So we can control the entire statistics. So based on this idea, we can define the control of Fokker-Planck equation. In this case, this is a convection diffusion equation where the control is in the drift. And we can ask a classical problem is to move the density from some initial distribution to the distribution desired. For example, suppose our quantum system starts with a distribution given by a Gaussian in the initial conditions, and this is a spin system. So there is a Gaussian distribution of the orientation of the spin in one direction, and you want to put this in mean, so in a Gauss distribution on, say, on the North Pole. No, you want to rotate this spin. This is what is done here. And this is essentially the setting. You have on the left, well, my left is on the equator, is where the system, the spin is oriented to. This is the block sphere. And then you want to put this on the South Pole, okay? And what is done? So you solve the control problem with the PDE, then you get these control functions are only time dependent, and then you verify by stochastic simulation with stochastic differential equations. You just simulate with this obtained control. And you see that here there are just few trajectories plotted. They start at the equator and they take very different trajectories. In fact, trajectory was not specified, the control problem, but they come all to the South Pole. So this, I think, is a very nice result that, okay, tells you about the open quantum system. Other problems transition quantum well, very classical. So you want to go from one energy level to another energy level, which means eigenfunctions with different frequencies. So this is a one-dimensional setting. And here I wanted to avoid to repeat you always the same thing. No, I tried in any slide to have something different. So what is different here is the formulation of the cost functional. In the cost functional I've shown you before, we have the L2 difference between the desired target and the final state obtained by the model. So this is a L2 difference. But in quantum mechanics, a phase difference of two vectors may be not relevant. So if you shift your desired state and the final state of your system by some phase, you actually are in the same place. So to remove this difficulty, which is given by the L2 distance, we take the projection, the projection in the complex scalar product. So what I mean is that by maximizing the scalar product of the desired state with my final state, I actually getting to the same. No, they are both normalized. So this would be a better choice for a functional for the tracking at the final time, for the final observation. Okay, just this comment. Well, I have another video here, but I think I avoid to make, I don't know. We have time? How much time we have?
Yeah, you have, let's say another 10, 15 minutes.
Okay, then let's go on this. I send you the video if you like, okay? Okay, so here there are results. This problem has been solved now with different methods, just steepest descent on the left, nonlinear conjugate gradient, and Newton scheme, Krylov-Newton scheme. So this is another message. There are many results in the early time of quantum control where people show very zigzag solutions because the criteria of convergence of their simple gradient method was 10 to minus 4. And if you do the same problem with a better solution method, say nonlinear conjugate gradient, and you gain another 2 order of magnitude in the precision of you get the minimum of your functional, this function will no more be so irregular zigzag, will look much better and more regular. And this is essential if you go to the experimentalist and you give something which makes sense, right? If you use a more sophisticated method like Krylov-Newton, then you get another, say, 4 order of magnitude, and your control function will be the right one, and it will do the right job. So there is a need to do good solvers. And I mean, Krylov is even not competing with steepest descent, so, or great. I mean, here we are in a much better kind of methodology. So try to convince your colleagues from physics not to use Krotov and Gray, okay? We have done linear models. Now let's talk about nonlinear models. One beautiful nonlinear model where there is a possibility to do a lot of experiments in the laboratory because it's like you have a cloud of, say, rubidium or the bosonic gas, and you can see exactly what they are doing, but they behave as a unique quantum particle, so you can see quantum phenomena like interference at a macroscopic level. So these are the Bose Einstein condensate. This is like a Schrödinger equation, but in addition, we have this mean field term, which is the square of psi. Okay. Also here, there is the need to design this experiment, and the control problem is, for example, to manipulate this cloud. For example, for doing interference, you want to split this cloud and then let it again interfere. So this is this kind of experiment I've considered in this case. What we do is we have a potential which is a quartic potential, is a confining potential, and then you want to split this cloud, which is inside this quartic potential. What you do? Well, you will do the same also by anything. You will try to take it and open, right? So this is exactly what this term x minus x squared is doing, is opening the cloud of the condensate, okay? This can be implemented in the laboratory by systems like this. So you can trap this Bose Einstein, and then by magnetic fields, you can open it, yeah? In fact, it's been done by Schidmeier in the Atomic Institute in Vienna. Okay, this was a control problem to cut, say, this cloud. You see, the functional is the one as I suggested in the last slide. So it's just about coherence and the projection of states, and the control is now only the time derivative. To remark is that the adjoint equation is here not a physical Bose-Einstein condensate at all. I mean, it's not about saying the adjoint is not physical. This is maybe a sentence that everybody says. But the fact is that we don't know, we have no analysis for this equation. I mean, every time you do control theory, you have to come up with problems, new problems, okay? Anyway, this optimal system has been solved by nonlinear conjugate gradient, and we get some control function. Beautiful is to see the result. So on the left, there is the standard used idea to make this quadratic cut by a function which is linear in time, increasing linearly in time. This is on the left, and you see the tracking at the end of the decided state is not very good. And on the right, it is the one obtained by optimization, where you get a perfect cut to the two states that decide to stay at the end, which is the ground state of the Bose Einstein condensate with this quartic quadratic potential. Okay. So more complicated and more used. So if you have if in your department there are computational chemistry people or people doing theory, theoretical chemistry, they most of the time have to do with time dependency function theory. Here the point is, how can we compute the molecule with many atoms, but we cannot use the Schrödinger equation with the B 3 times n space variables dimension would be intractable. So the idea is actually here to construct instead a system of lower order Schrödinger equation with a nonlinearity which makes the link so that these states computed by these single equations can be combined to give the same state as this high dimensional problem. This is a fantastic idea that explained why Kohn and Sham received the Nobel Prize for this work. So here again, we have a system of Schrödinger-like equations with a Kohn-Sham potential, which makes like the link, and this Kohn-Sham potential has this structure. Now, we don't have time to look through this, but as you see, there is some remembrance of the Bose Einstein condensate. This rho is the sum of the square of these single wave functions, okay? So in this field, it is even not clear for all molecules how to write the potential and how to set up this exchange potential Vx and Vc. Here there is a lot to do for the next 50 years. Even theoretically, it's not all clear. And numerically, it's also a big challenge, a really big challenge. A system of Schrödinger equation nonlinear in 3 dimensions. So it takes some work to do. And in this case, I've considered for low dimension, the case of tracking a density, getting to a final time, or even something that moving the density from one side to the other. So there is some work done, but I would say this is just very low dimension, and it would be nice to embark in something like this in more, say, systematic way. And but the beauty is you can show it works and it does what the control function is required to do. Okay, see, I think this is just to tell you that one field of quantum mechanics, which is less explored, is the statistical quantum mechanics approach. In this case, there is also the Wigner equation, which, as I told you, it's similar but not equal to a Vlasov, where you have a convective part, which is standard, like in Vlasov, but they have a pseudo operator, differential operator, for the, say, the interaction with the control field. Anyway, it is written maybe too complicated, but this is very much investigated in semiconductors. And also here we can think of functionals, for example, of statistical physics, of ensemble functionals. So this F, if you interpret F as a density probability function in the phase space, then phi F, the integral, is the mean value of the phi function, no? in the phase space. Okay, so this is one of the last things I've considered together with friends in Florence, yeah, Firenze, and we have done some theory of this and very small problem being considered. So there's much to do in this direction from many points of view: discretization schemes, numerical solution, numerical methods. It's a lot to do, and this is just a simple particle. Then it can be with spins, more charges, different species. Okay, I think I'm come to the end. So there is a lot to do. I think I could tell you this, and things that should, in my opinion, could be done, but not for quantum computing, is consider the relativistic setting, a quantum field theory. This would be of interest for theoretical physics, so people who do high energy physics. The quantum statistical framework is, I guess, the most important for future design of devices and applications. There is a lot to do. For example, a keyword today is Hamilton identification, how to identify the Hamiltonian, to set up a proper design of an experiment. And then there are infinite number of functional and numerical analysis issues. So I think I am in time to conclude now. Thank you.
Thank you very much, Alfio. That was very informative. I have a whole bunch of questions in case maybe I should just start. So I guess on a theoretical perspective, it seems like you often use traditional techniques from optimal control of PDEs. On the other hand, some of the models are a bit more complex than, let's say, we're used to encountering, especially based on the fact that you have complex valued solutions and things like that. So I was wondering, when you first showed that Lagrangian way back, maybe page 10 or so, if it's really so clear that, let's say, Lagrange multipliers exist, if you have, let's say, surjectivity of the linearization of the differential operator and things like that. Does that all kind of go through like usual, or are there tricks there that have to be considered?
Well, I can say that for the models with the Liouville von Neumann, so the finite dimensional models,
yeah,
from the standard linear Schrödinger model with controlled dipole, the answer is yes, it has been proved. And it is the standard arguments.
Yeah.
For the DFT, the time-dependent density function theory, I don't know of myself proving this. There is, we have only partial results, I would say. So this is not covering the nonlinear cases, for example.
Oh, I see. Okay.
So in this case, I would say it's an open issue for the DFT for sure. Yes. Hello, Lars.
And I guess so along these lines, you often use tracking type functionals or this alternative functional.
Yeah.
But like when you do control of Fokker-Planck and you're trying to sort of match densities, wouldn't it make more sense to use something like a divergence, for example, like a Kullback-Leibler?
Yes, yes, for sure. Well, actually, there is a work that has never been completed with the recent class on about analyzing different Wasserstein distances, Kullbach, Leibler, etc. I've recently used this in other work, which is not about a quantum. Yes, for densities, in the sense of tracking densities, the Kullbach-Leibler would be more appropriate, but you must take care of which kind of density. So if it is density of probability type, like in the Fokker-Planck, would be this is a good choice, very good choice. For in quantum, it depends. It is material density, it must be adapted, or it is much more useful to use much more, say, convenient to use. I show you what I call ensemble functionals. If I come to that, it should be the next slide. Where is it? Yes, ensemble functionals, where I told to make like statistical functionals, so like average functionals here. And here the problem is how to get to second moments or things like this. No?
Yeah.
But the short answer, yes, Kullbach-Leibler is a good choice for comparing densities. Yeah.
So Adrian, do you have any questions? Maybe?
Yeah. So maybe like so you mentioned that there are these 9 different mathematical formulations.
Yeah.
For example, for the Schrödinger equation formulation, is there any like there's a lot of like mathematical formalism or mathematical structure. Is there anything that's for example that is good for optimal control, or anything that's very like that's not good that you noticed?
Yes, I think that it would be nice to have a paper, say, quite abstract, take any simple model and try to formulate the same control problem with all these formulations.
Yeah.
It will not be so trivial because in one, you have the state, so maybe the Schrödinger formalism is the best one. And the other, you have observables, so maybe the Heisenberg formalism would be the better one, etc. So there is the pilot wave, the Jacobi approach. So what I want to say is any formalism is maybe focusing on a representation of the system, so that when you go to write what you want of this system, maybe there are difficulties or maybe it's better. And I personally have not done this, but I would be very happy if someone goes through all this and says, oh, look, even for this simple, say, control of spin, just one spin rotation or whatever in the block sphere, what happens with a different formalism? It'd be very nice. Yeah.
Thanks.
Yeah.
Sölva or Professor Grüner, do you have any questions? No? Okay, great. Then let me just stop recording for a second. Thank you again, Alfio.
Yes, you are welcome.